Hi, I'm David Bonsack, Product Manager for Rheology at TA Instruments. I would like to welcome you and thank you for joining us for today's webinar. If you get disconnected at any time, please use the instructions you received to log back in. You can access additional content by clicking the Documents icon at the bottom right-hand corner of your screen. This includes speaker bios and related file downloads. And if you need help at any time, click the question mark icon. Please ask any questions you may have at any time during the presentation by submitting them through the Q&A window. We will answer as many of these as possible at the end of the webinar. Our guest presenter today is Dr. Terri Chen. Dr. Chen is a Senior Applications Support Scientist with TA Instruments, supporting rheology and DMA. She received her PhD in Polymer Science from Sun Yat-sen University in China, specializing in polymer synthesis and characterization. She then moved to the University of Maryland, where she was first a postdoctoral researcher and later a research assistant professor working in the area of biopolymer modification and analysis. Dr. Chen joined TA Instruments in 2004, where she provides customer support, consultation, and training. Dr. Chen has more than 50 publications in peer-reviewed journals and 2 U.S. patents. Today, Terri will share some of her experience in using rheology to test and understand the performance of adhesives. The title of her talk today is Strategies for Rheological Evaluation of Adhesives. Terri?
Hello everyone, welcome to TA Instruments webinar. Our today's topic is on strategies for rheological evaluation of adhesives. Here is our today's agenda. First, we will give a basic introduction on rheology and rheological methodologies. Then we will discuss experimental designs to correlate with adhesive properties. Specifically, we will talk about viscosity measurement, Tack and peel tests on rheometers, how to set up a dynamic time sweep to monitor curing, and then we will discuss how to design a good temperature ramp experiment, how to use frequency sweep and TTS results to correlate the end product properties, and how to use creep test and creep TTS to predict shear resistance and cold flow. At the end, we will introduce the benefit of using rheology interconversions. First of all, what is rheology? Rheology is the science of flow and deformation of matter. Rheology studies the relationship between a stress and a deformation. When you apply a stress to a purely solid, elastic material, such as a spring, you will find out that the stress you applied is linearly proportional to its deformation, which is the strain. The ratio of stress over strain is defined as the modulus of the material. When you apply a stress to a purely liquid, viscous material, such as water in a dashpot, you will see that the stress is linearly proportional to the rate of the deformation, which we call it shear rate. The ratio of stress over shear rate is defined as the viscosity of this material. Most of the materials we work on our daily basis, such as adhesives, have both elastic and viscous properties. Therefore, these kind of materials are viscoelastic. Rheology analysis plays a big role in adhesive industries. The rheological analysis results can be used to directly guide synthesis and formulation, help to troubleshooting processing problems, and also provide quantitative evaluations to the final product performance. First of all, rheology test results can be used to quantify molecular weight and molecular weight distribution of the base polymer in adhesives. Compare differences in polymer structures such as branching or cross-linking. It also helps to compare differences between formulations. Second, rheology tests can also help to guide processing conditions. For example, in adhesive coating process, rheology measures shear viscosity of adhesive solutions or how it melts. It helps to guide the application's rolling speed. In adhesive curing, Rheology test results can help to optimize the curing conditions, such as temperature, humidity, or UV intensity. In addition, rheology can also quantitatively measure the end product performance. The measured rheological parameters can be used to directly correlate with adhesive, cohesive strengths, and also elasticity. This table listed 4 commonly used rheological tests in adhesive analysis. First, a steady flow test can measure shear viscosity over a wide range of shear rate. The axial testing on a rheometer is typically used for measured tack and peel. The dynamic oscillatory tests are the most popularly used tests in adhesive analysis. First, this measurement measures the transition temperatures, such as glass transition. Also, the measured parameters, such as G', G double prime, or tangent delta, are directly used to correlate with the adhesive performance. A creep experiment can also be applied to directly measure the shear resistance, how good of an adhesive to resist to a cold flow over time. For people who are working with adhesive coating process, a steady shear flow viscosity measurement can be helpful to guide the processing conditions. For example, pressure-sensitive adhesives are traditionally processed in 2 major methods: solvent coating or hot melt coating. This following figure shows a correlation of sample viscosity measured at different shear rate versus their properties and applications. The viscosity measured at low shear can help to compare and predict stability, how stable a formulation can be against sagging or sedimentation. Viscosity measured at medium shear correlates to a liquid sample mixing and transportation, such as pumping or pipe flow. The high shear viscosity measurement directly correlates to the coating applications conditions. Here is an example of 2 water-based adhesive formulations. Formulation A is more shear thinning, and formulation B is more Newtonian. So under low shear rate, formulation A shows much higher viscosity than B, which indicates that A potentially should have better storage stability against phase separation and sedimentation. Both formulations have similar viscosity at medium shear. But since A is more shear thinning, at the application high shear rate, formulation A shows much lower viscosity compared to formulation B. This means A potentially could spread easily and coat thinner layers. One of the most commonly used methods for evaluating the tack performance of a pressure-sensitive adhesive is described in ASTM D2979. This test can be conducted on a rotational rheometer using an 8 mm parallel plate geometry. We plate the sample between 2 parallel plates, apply a certain pressure for a short time, and then we pull off the plate with a speed of a certain millimeter per second, such as 0.1 millimeter per second. The maximum force that is required to pull the plate away is defined as the sample tackiness. In this type of test, breaking may occur in 3 different ways. If the bound force at the interface is stronger than the cohesion strength of the adhesive, breakage will occur between adhesive layers. If the cohesion strength is much stronger than the adhesion bound at the interface, then breakage will occur at the plate interface. Sometimes there will be a mixed breakage of both cohesion and adhesion. This following figure shows the tack testing results of a non-cross-linked and a cross-linked PSA sample. The cross-linked PSA shows significantly higher cohesion strength due to the introduction of a cross-linking network. Therefore, failure occurred at the interface. The non-cross-linked PSA, however, has weaker cohesion bound, so failure was observed to be between the adhesive polymer layers. Peel tests are usually conducted at different peel angles, such as 90 degrees or 180 degrees. Using a SER geometry on a rotational rheometer, we can easily perform the peel test at 180 degrees. The peel strength can be measured at different peel rate and also with different temperature. Dynamic oscillatory tests are the most commonly used rheological test in adhesive evaluations. In an oscillatory test, a sinusoidal stress is applied to the sample with a certain frequency. The sample response in deformation is monitored and recorded. If the input stress is within the linear viscoelastic region of the material, then the output strain should also be in a sinusoidal waveform. The shift between the input stress and the output strain is the phase angle, which is used to describe the viscoelasticity property of the material. In an oscillatory test, the commonly reported parameters are G star, G prime, G double prime, and tangent delta. This slide shows all of the equations for calculating those parameters from rheological testing. G star is the complex modulus. It is calculated from the ratio of complex stress over strain. G star can be separated into two components, which are G prime and G double prime. G prime is the storage modulus. People also call that elastic modulus. It measures the elastic response of a material, the ability of the material to store energy. G double prime is the loss modulus. People also call that viscous modulus. It measures the ability of the material to dissipate energy, how much energy is lost as heat in an oscillation. Tangent delta is the ratio of G double prime over G prime. It measures the material's damping property, such as vibration or sound damping. All of these parameters follows this triangle relationship, which is shown in this slide. In many of those adhesive books and papers, people have provided information on how to correlate the dynamic testing results to the performance of adhesives. For example, the storage modulus G prime correlates to the cohesive strength of the material. It describes the bulk property of the adhesive. A higher G prime at high frequency, which correlates to high shear, indicates high peel strength. A high G prime at low frequency, which correlates to a long time, indicates a good cohesive shear resistance. The loss modulus, G double prime, describes the viscous response of the material. So it correlates to the adhesive property at the interface. A high G double prime at high frequency correlates to high adhesive peel strength at the interface. A high G double prime at low frequency correlates to a high adhesive shear resistance. Tangent delta is the ratio of G double prime over G prime. It measures the elasticity of a material. Low tan delta means sample has good elasticity and high cohesive strength. A high tan delta means sample is more damping and potentially have high adhesive strength. So how many different types of oscillatory experiment we can run? And what kind of information we can obtain out of each test? Here, we have listed some typical dynamic test methods and their applications. First of all, a strain sweep or stress sweep experiment helps to measure material's linear viscoelastic region. It helps us to determine what strain to use for all other dynamic testing. A dynamic time sweep is commonly used to monitor curing. The curing can be monitored under a controlled temperature, humidity, or under a certain UV intensity. Dynamic frequency sweep provide direct correlation to samples' tack, peel, and shear resistance information as a function of frequency or time. A frequency sweep experiment running on a polymer melt sample can also provide information on polymers' molecular weight and molecular weight distribution. The dynamic temperature ramp experiment is probably the most popular test in adhesive evaluations. It measures transition temperatures and also provides information of adhesives' operating temperature range. Many adhesives are cured or partially cured through heat, UV radiation, or under humidity. A dynamic time sweep experiment is typically used for monitor curing. This following figure shows an example of using a UV curing accessory attached to a DHR rheometer. The UV light with a controlled intensity was triggered on after 25 seconds of equilibration, and then it was remain on for 30 seconds. During this entire time, the modulus change of 5 different formulations was monitored. This type of rheological test allows us to quantitatively measure adhesives curing with different formulations, different controlled UV intensity, and also at different temperatures. In most cases, when material cures, they shrink in dimension. Adhesive curing shrinkage will cause product failure during the process. Using a rheometer with UV curing accessory, we can quantitatively monitor this shrinking phenomenon. As we can see from the figure on the left side of this slide, if we fixed the measurement gap during the measurement, we can quantitatively monitor the axial force buildup during curing, which is shown in the blue curve. For this particular sample, the force increased up to almost 15 Newton across a 20 millimeter diameter plate. And then after the curing is completed, the force slowly relaxed over time. If we actively release this shrinking force to 0 during curing, then we can monitor sample dimension change. The blue curve on the right side of this figure shows how much the gap reduced during curing. The silicone-based adhesive curing is sensitive to the environmental humidity. Using a rheometer with a humidity control chamber, we can monitor the curing process with a controlled temperature and also humidity. This graph shows an example of monitoring a silicone caulk curing under different humidity level. The results have shown that this sample cures much faster under a higher humidity environment. Dynamic time sweep experiment is probably the most popular test in adhesive evaluations. This figure shows an example of a non-cross-linked pressure-sensitive adhesive temperature ramp results. This test provides many information to the performance of this adhesive. First of all, glass transition, TG, is observed at 16.3 degrees based on the location of the 10 delta peak. Below glass transition, the sample is hard and brittle and has no tackiness. So the glass transition temperature is usually considered as the lowest application temperatures of a PSA. Above TG, sample softens and the modulus drops significantly. The sample behaves in a viscoelastic manner. At even higher temperatures, a non-cross-linked PSA will molten. This can be observed at the highest G', G" crossover temperature, which we described as Tx in this figure. For this measured adhesive, the Tx is observed to be at 75.9 degrees. Above this temperature, adhesive flows like liquid and totally lose cohesive strength. In general, the application temperature window of an adhesive should be between Tg and Tx. In adhesive industry, sometimes people also use the Dahlquist criteria to describe and define applications window. The Dahlquist criterion states that the modulus of an adhesive should be between 50 to 300 kilopascal. When higher, the adhesive has difficulty wetting the substrate. But if lower, the adhesive has low shear resistance. So in certain applications, this TD is considered as the lower temperature limit for the application of an adhesive to a substrate. In addition to measure transition temperatures, this temperature ramp experiment also provides information on sample modulus. The rubbery plateau moduli, G', G', are also commonly used to evaluate the cohesive and adhesive strengths of an adhesive. The dynamic temperature ramp experiment on adhesive-based polymers can also be used to compare polymer molecular architectures, such as molecular weight distribution, and cross-linking. For example, when testing the same type of adhesive polymers with different molecular weight, one will observe that if the polymer has lower molecular weight, and then it will show a shorter rubbery plateau region in a temperature ramp experiment. If after glass transition, the polymer shows a continuous decrease in G' or G' instead of having a relatively flat rubbery plateau region, then it indicates that this polymer may have a broader molecular weight distribution. If the polymer is cross-linked, first, it will show a higher Tg compared to the same polymer that is not cross-linked. Also, the rubbery plateau modulus of a cross-linked polymer will be higher. The shape of the curve will be more flat and extend to much higher temperatures. A cross-linked polymer will never molten. In some literatures, people use the rubbery plateau modulus value to quantitatively calculate the degree of cross-linking. Here is the summary of the polymer structural information we can obtain from a temperature ramp experiment. As we can see, when we perform a temperature ramp experiment from below glass transition until up to molten state, the modulus of the material changes over 5 to 7 decades. It goes from glass-like solid all the way to honey-like liquid. In this case, it is very challenging to use one single size geometry in one continuous procedure to obtain a good temperature ramp results. Here, I would like to introduce some guidance for a good temperature ramp experimental design. First of all, it is always good to load the sample at higher temperatures because the sample will be soft or molten so that it will be easy to trim. The most commonly used geometry for testing a PSA sample is the 8mm parallel plate. If you do not intend to go through glass transition, a 25mm plate is also okay to be used. The measurement temperature is usually going from below the glass transition till the sample is molten or before it degrades. The commonly used heating rate is at 2 to 5 degrees per minute, and the commonly used frequency is at 1 Hz, or some people use 10 radians per second. The most challenging parameter setup is on the sample strain. Strain needs to be within the linear viscoelastic region of the sample. When sample undergo such a big change in physical property, it is important to have the capability of adjusting the strain during a temperature ramp experiment. In addition, both sample and geometry will expand or shrink as we change temperature. So it is important to have active axial force control to avoid sample slipping and also compensate for sample and geometry expansion and shrinkage. As we have just mentioned, Setting up a good strain is the key for getting a good temperature ramp experimental results. So how do we decide what strain to use for a certain sample testing? This figure shows a series of strain sweep tests at different temperatures from below glass transition until above glass transition. First, let's look at the red curves, which is the strain sweep at minus 30 degrees C. As we can see, below glass transition, sample modulus is high, and at a strain of 1%, this measurement maxes out the instrument torque. It means that we are not able to go any strain higher than 1 to 2%. Also, below glass transition, sample is fragile. Using a large strain may crack the sample. Therefore, at low measurement temperature, using a smaller strain is preferred. Then let's look at the black curve on the bottom of this figure. This is the strain sweep experiment at 50 degrees C, which is above the glass transition. At this temperature, sample is really soft and has low modulus. A 1% strain will get a torque of less than 10 micronewton-meter. So in this case, using a large strain will be preferred because small strains will result in some noisy data if your instrument is not on a perfect anti-vibration bench. Then the question is, how do we change the strain in the middle of a temperature ramp experiment? Different rheometers and different softwares using different methods to alter the measurement strain in the middle of a test. If you're using one of TA Instruments rheometers, such as a DHR or Aries G2 rheometer, there are two ways for adjusting the strain. One method is called auto strain. This method is good for both DHR and Aries users. As you can see from the screenshot on the left side, this method asks the operator to set up a torque window during a test. This torque window is not the instrument spec. It is particularly selected based on the fact that the measurement is within the linear viscoelastic region of the sample and also ensure a good signal-to-noise ratio. When the test strain requires the torque that is outside of this window, strain will be adjusted. The other method is for the DHR user. It shows on the right side of the slides. In the main temperature ramp experimental procedure, operator enters a small strain that is in the linear viscoelastic region for the entire test. And then, under Control Strain Advanced tab, selecting non-iterative sampling, the software requires the operator to enter a lower torque limit. This lower torque limit is not the instrument low torque spec, but it is a smart way to help adjusting the strain when sample becomes really soft. Now let's take a look at an example in the next slides. This is a temperature ramp experiment on a non-crosslink PSA sample. The measurement is from minus 30 degrees C up to 100 degrees C with a heating rate of 3 degrees per minute. The initial test strain was set at 0.05%, which was within the linear viscoelastic region of this sample and also appropriate for the measurement at the initial low temperatures. As the temperature increased up to above the glass transition, sample became a lot softer. The torque to control a 0.05% strain was reduced significantly. When the torque hit this lower torque limit, which in this case we set it at 2 micronewton-meter, the instrument automatically switched to use a torque control for the measurement. From this particular point up to higher temperatures, the measurement torque was fixed at 2 micronewton-meter. So strain, in this case, will continuously increase as the sample gets softer. But this strain will still be within the linear viscoelastic region. This method allows automatic strain adjustment and gives very good measurement results for all temperature ramp experiments for adhesives. The dynamic temperature sweep experiment is commonly used to evaluate the performance of end product. High frequency modulus correlates to peel stress, and the low frequency modulus correlates to shear resistance. The modulus at medium frequency measures the performance of the adhesive. However, the maximum frequency a rotational rheometer can reach in one single test is only 100 Hz, which is 628 radians per second. This may not be high enough to mimic a certain high shear situation. Also, low-frequency data may require days or years to collect, which makes the measurement practically impossible. In this case, a time-temperature superposition technique can be explored to extend this measurement frequency range. Time-temperature superposition is a very useful theory. It is based on the observation that for a thermal rheologically simple material, the viscoelastic property generated at different temperatures are equivalent to the properties measured over a broad time or frequency scales. For example, in a dynamic testing, frequency sweep data collected under different temperature steps can be horizontally shifted along the x-axis, which is the frequency. After you select a reference temperature, any low temperature data will shift to high frequencies, and the high temperature data will shift to low frequencies. This allows access to a wide range of frequency, which is outside of the instrument capability. In addition to dynamic testing, time-temperature superposition can also be applied to transient tests, such as stress relaxation or creep. The figure on the left side of this slide is an example of a TTS data on a non-cross-linked PSA sample. The reference temperature was selected at 20 degrees C. If you put this TTS master curve side by side with the dynamic temperature ramp data, you will easily see that these two results looks like a mirror image. This is the principle of time-temperature effect. This figure shows the overlay TTS master curves of a non-cross-linked and a cross-linked PSA sample. The reference temperature was selected at 20 degrees C. From these test results, we can quantitatively compare the tack, peel, and shear resistance performance of these two types of adhesives. Alternatively, shear resistance property can also be evaluated using a transient experiment, which is a creep test. Actually, creep is a more intuitive method to monitor cold flow of an adhesive. In a creep test, a constant stress is applied to the sample instantaneously and held for a certain period of time. During this time, the change of strain is monitored. Sample compliance is calculated from the ratio of strain over stress. In order to predict shear resistant property of an adhesive over a long time, such as months or years long, a creep TTS experiment can be performed. It is a multiple-step creep experiment conducted at elevated temperatures starting from your reference temperature. The high-temperature creep results can be shifted and also used to predict long-term performance. Here is an overlay of two creep TTS results of a non-cross-linked and a cross-linked PSA sample. Each TTS test takes only about 1 hour long, but the analysis results can be used to predict the property of over 10 to 12 days. From these measurement results, we can clearly see that the non-crosslink adhesive has significant creep over time. It displays poor shear resistance to a cold flow. In the last section of our today's talk, I would like to introduce the concept of using rheology interconversion. Any materials in the world only has one set of linear viscoelastic properties. Within the linear viscoelastic region, the rheological properties of a material can be interconverted from dynamic to transient properties through relaxation and retardation spectrum calculations. This following chart shows the conversion route between dynamic and transient tests, such as stress relaxation or creep. TA Instruments Trio software can easily help the users to perform this kind of transformation calculation. So using this interconversion calculation, we can directly convert our dynamic TTS data into a transient creep data. So there is no need to perform two sets of separate TTS experiments. This interconversion technique helps us significantly save the experimental time. Here, let us summarize our today's talk. Rheology is a powerful technique that is widely used in adhesive industries. The rheological analysis can provide useful information on adhesive polymers' structure-property relationship, guide adhesive processing, and also quantitatively evaluate the end product performance. Designing and selecting appropriate rheological test method and parameters are important to ensure good measurement and also accurate correlation to the adhesive properties. With this, I would like to conclude our today's talk. Thank you very much for your attention, and I'll be very happy to take any questions.
Thank you, Terry, for that informative presentation. A recorded version of this webinar will be archived and made available through the TA Instruments website. We will now begin the question and answer segment of this webinar. If you haven't already, please submit any questions you may have using the Q&A window. We will do our best to answer as many of these as possible. All right, we have some questions that are coming through. So the first question is related to the measurement of the glass transition temperature, or TG. And can you repeat and discuss why it's necessary to use 8mm plates in order to accurately measure the TG and the modulus through the TG?
Oh, yes, that is a very popular question most people would like to ask. Well, actually, when you go measure an adhesive material through the glass transition, especially below the TG, the sample modulus is high, the sample is really, really stiff. If you put that sample between a larger diameter plate and twist it, so very possibly, okay, you may end up getting, a lots of compliance issue on generally instruments, and also the sample may get cracked, and the torque may be extremely high. So that's why for most of the cases when people evaluate the temperature performance of adhesive through the TG, 8mm plate is the most commonly used.
Okay, perfect. Moving on to the next, there's a question referring back to earlier in your remarks when you were talking about making Tack measurements. Is it possible to calculate the Tack energy from a Tack test, and if so, how would you do that?
For the Tack measurement, we designed the measurement based on the ASTM procedure. So what I saw actually from some literature is that people have been trying to use the area. They take the area between those, the Tack testing curves and consider to use that to calculate the Tack energy. So that's what some literature reported.
Okay, perfect. So using the area under the curve. Next, can you comment on when is it better to use dynamic testing rather than creep testing, and under what conditions or what adhesive properties would you be looking for in which you choose dynamic testing rather than creep testing?
That's a good question. Typically, people design the creep experiment because creep is actually a most intuitive type of measurement to evaluate shear resistance and cold flow. So based on the characteristic, based on the nature of the test. Basically, you apply a constant load to the sample and monitor the sample deformation change over time. So that, when people really the goal of the measurement is to evaluate shear resistance or cold flow, and that in that cases, people mostly select to use a creep test. But the majority of the cases, when people evaluate viscoelastic property, and people prefer to use dynamic testing. So in dynamic testing, they use moduli, G prime, G double prime, to correlate with adhesive and cohesive strengths. They use tangent delta to correlate with the material's elasticity. And that's why they, dynamic testing is more popularly used. However, based on the last section of my talk, you can see actually creep testing and dynamic testing, they are interchangeable. As long as you perform the measurement within linear viscoelasticity region, you can actually calculate back and forth from a transient test to dynamic test, or from a dynamic test to transient test.
Okay, very good. We have a number of questions about TTS. Let's talk about just two of them. So one is, I guess, to the mechanics of TTS. First, in TTS, you can do both vertical as well as horizontal shifting. So when would you want to do a vertical shift? And then following on to the applications of TTS, is it possible to predict time or performance of materials over longer times through TTS?
The general principles for time temperature superposition analysis is mainly on horizontal shift, which means you shift your physical viscoelasticity property along x-axis, which can be frequency or time. For vertical shift, which people still do because not everything perfectly fit with the TTS theory. So the fundamental theory for talking about TTS is like your material needs to be thermo-rheologically simple. But over the years, people overuse this TTS, for their material, which is, for example, like highly branched or partially cross-linked or partially filled. So those samples may not be perfectly fit with the fundamental time temperature superposition theory. So in that cases, people needs to perform a certain type of vertical shift, and the software allows you to do so. But the vertical shift, it is available, you can do that, and you can also do manual shift to get the best overlap of different temperature steps. Okay,
very good. Here's a question about zero shear viscosity. Would you use zero shear viscosity to predict adhesive performance? And if so, what characteristics of the adhesive performance would you use or would you predict using the zero shear viscosity?
Zero shear viscosity is commonly used, obtained. First of all, how do we measure zero shear viscosity, right? So zero shear viscosity can be obtained through a viscosity measurement from low shear rate up to a medium or high shear, right? After you finish the test, you can extrapolate your viscosity curve down to really, really low shear and eventually get to shear rate equals to 0. So that zero shear viscosity property is usually used to compare different formulations. In general, a higher zero shear viscosity is commonly used to, is considered as the sample is more viscous when you don't shear, so potentially it should have better stability, storage stability. So this particular formulation potentially will be more resistant to phase separation over time, will give you better storage stability.
Okay, that's great. And that ties in with another question, and maybe you can elaborate. So the question is, how would you measure the stability of an emulsion? Is it really the zero shear viscosity, or are there any other means that you would use to look at stability of an emulsion?
For emulsion, there are multiple factors that people use to correlate to stability because, so first of all is zero shear viscosity help you to predict when you don't shear, or in the storage condition, which one potentially can be more stable. And there's another thing is related with stability is what is the yield stress of this emulsion. Okay, so as you start to shear the sample, if the sample yield stress is high, potentially it will be more resistance to any potential shear or vibration situation. So I would say to talk about emulsion stability, I would use, multiple factors to correlate the stability. Number one, zero shear, or low shear viscosity. Number two, yield stress of the material, and also thixotropy properties, how fast the structure can recover. Because after you shear your breakdown structure, if the structure recovery takes too long of time, the sample may also be considered as non-stable. With that, actually, on TA Instruments website, we have some other webinars talking about how to evaluate yield stress and also thixotropy.
Okay, perfect. There have been a few people who have asked questions about the practical sample thickness. Can you give some guidelines as to what are common sample thicknesses when you're measuring, and then beyond what's common, is there a minimum thickness that you would advise, and any recommendations that you can give there?
Oh, yes. Over the years, actually, when I work with adhesive industry people, they always like to ask the question about what is the sample thickness and how do we do this rheological measurement. Say it this way. Rheology, we measure the bulk property of the adhesive itself. Typically, especially for, for example, pressure-sensitive adhesive. Usually, I would recommend the user to collect enough sample, which means, peel the sample off the backing, collect enough sample. The most commonly used measurement gap that people use in the rheological measurement is with a sample thickness about half a millimeter to about 2 millimeters. So that's the most popular rheological testing sample thickness in the parallel plate testing. There could be certain situations that the sample is really thin. As long as you do not attempt to pass the glass transition, and that can still be doable. I was just saying that, the most popular, most commonly used sample thickness, and which is also correlates to the geometry gap, is half a millimeter to 2 millimeter.
Okay, great. We've had a lot of questions, but only time for about 2 more questions. So the next question follows on to the theme of stability that you were addressing earlier, and the question is not about emulsion stability, but about filler stability. And can you give any insight into gauging filled materials and the resistance of filler settling out of a suspension over time?
The filler suspension over time?
That's correct, yeah.
That has something to do with the yield stress measurement, okay? Filler is actually, most of the fillers are, is kind of like a suspension. They suspend it in the liquid system. So to evaluate the stability of that, most people use the yield stress measurement to get a good correlation.
Okay, perfect. And the last question today will be, can you discuss cold flow, and how would you predict cold flow using rheology?
The cold flow has something to, to predict cold flow, most people use creep experiment. So for cold flow is like, when you apply a load onto the sample and see how much the sample flows over time. That is exactly what creep experiment will do. So to predict cold flow, a creep experiment will be the way to go.
Okay, perfect. Well, thank you very much, Terri. This concludes today's program. I'd like to thank you, Terri, for spending some of your time with us today and sharing some of your experience in testing adhesives. And I'd also like to thank all of you in the audience for joining us today. This webinar, like all TA webinars, will be archived and available through the TA Instruments website. Please look out for invitations to future webinars, and be sure to check out our other archived webinars and online training courses that are available through the TA Instruments website. Thank you all, and have a great day.